Let us discuss now the input impedance of a buck converter and see how the input impedance of a buck converter can be regulated by duty cycle control. Consider this PV module and let us interface this PV module or the PV cell to a buck converter. So the buck converter consists of a BJT switch like this. This BJT can be replaced with a MOSFET switch, or it can also be replaced with a IGBT switch. And this is followed by a diode connected in shunt like this. We have an inductor and a capacitor. So this would form a buck converter circuit, this portion. Now to that, let us connect the load or not. So we have the load, and that is R0. The voltage across R0 is V0, and the current flowing through R0 will be I0. So let us have the symbols as indicated. This is C, L, D, Q. Q is the switch, and here you have the terminal voltage VT across the panel and the current IT flowing out of the terminals of the panel. So this is the buck regulator circuit connected to the PV module. In the boost converter, connecting a capacitor across the terminals of the PV panel is not mandatory, though it will be helpful. But in the case of the buck converter, here connecting a capacitance here is mandatory. It has to be connected. I will connect that later after discussing why. For now, let us understand the operation of the circuit and try to find the input-output voltage relationship, input-output current relationship, and the input-output resistance relationship. Let us have this set of graphs. So one axis here, the x-axis, which is the time, and the y-axis VL. VL is the voltage across the inductor, and it is measured like this with a common point of the probe on this end of the inductor and the positive end of the probe at this point. And we shall also have one axis versus time for the current IL, the inductor current. These are important variables and parameters that we need to observe, which we will use for analysis later. Let us mark the time spaces. So I will mark the time spaces like this. Now this portion is the time when Q is on, and I will call it as DTS, like we did in earlier case for the boost converter. This is 1 minus DTS. Together this period is TS period because D is less than 1. Now it will repeat for the second TS period also, like this. Now we can use this for drawing the waveforms. During the time DTS, Q is on. During 1 minus DTS, Q is off. So we will indicate that this is the on time, off time. In the next cycle, again on time, off time, and so on. So when Q is on, what happens? We will have the current flow in this fashion. Q is on, so this node is connected. This node potential is the same as this node potential. So this is VT, this is positive, diode is reverse biased, it is out of the picture. Q is on, so you have the current flowing like this through the inductor. Part of it goes into the capacitance, another part goes through the load I0 and comes back. So this is the current flow through the circuit when Q is on. So when Q is on during the DTS portion, so during this time period, let us see how the waveforms look like. The voltage across VL first. This node of the inductor is at potential VT because Q is on, diode is off. This and this will have the same potential, so that will be VT. This potential is connected to the output, therefore this is at V0. So the voltage across the inductance VL will be VT minus V0. So that is what we will have here, VT minus V0. So let us shade that. And the current through the inductor is flowing in this fashion. As I said, this is more positive than this. As shown in this graph, the current will rise up linearly. Vt minus V0 is constant, and because VL is equal to L dIL by dt, IL is an integral, it rises up with a slope Vt minus V0 by L. So it will be like this, and I will add one more axis like this, and that is to see what is the terminal current like. So this is terminal current IT, and because this is coming in series with the inductance at this point, because diode is out of the picture, the inductor current is same as Q current, same as IT, and therefore IT and the inductor current will look same. During 1 minus DTS period, Q is off. So when Q is off, there is no current flowing out of the terminal of the PV, and the current through the inductor cannot stop. It has to continue, and part of it goes into the capacitor, part into the load with appropriate directions, and then you see that it freewheels in this fashion through the diode. Diode is now on. So under this operating mode, let us see how the waveforms develop. The voltage across the inductor during this mode of operation is minus V0. That is because this node is connected to the ground, so this potential is 0. This node is at V0 potential, so 0 minus V0 will become minus V0. So you will have a negative voltage across the inductor minus V0. This again is expected because we want the positive voltage and the negative voltage to balance within the cycle such that the average voltage across the inductor should be 0 in the steady state. And the inductor current, see, the voltage across the inductor is minus V0, and therefore the inductor current is now discharging, falling down with a negative slope of minus V0 by L, because VL is equal to L di by dt. The slope dIL by dt will have a falling slope of minus V0 by L. So this would be the inductor current within the cycle. IT, because Q is off, there is no current flow from the terminal of the PV panel, so this remains 0. So this repeats this cycle also. So you will see that the voltage will be a repetition cycle by cycle, so on. The inductor current and the terminal current of the PV panel will look like this. Now if you take the average of the inductor current, so the average of the inductor current, the DC equivalent of the inductor current, is flowing through R naught. That will be pure DC, V naught by R naught. So that is equal to I naught. The ripple portion, which is having an average about this DC as 0, will flow through the capacitor, because the capacitor should have a 0 average. So the AC part, the ripple part, having a 0 average, flows through the capacitance, and the DC part flows through R naught. So therefore we know that this value here right through the middle would be having a value R naught, I naught in the waveform of IT, that is the terminal current. Observe that the terminal current is not continuous, it is switched, broken up. Okay. So if it is switched and broken up, when IT is flowing, the power is some finite value. When IT is 0, during this time, IT is 0, which means the power drawn from the panel is 0, which means you are underutilizing the panel. For the panel to be delivering peak power, we need IT to flow continuously. So now what is the continuous equivalent of IT here? So this would be the average value of this. So let us say the average value of IT, I will call that as IT average, is the DC value or the average value of this switched waveform, current waveform. And this average value has a value like this: IT average is equal to I naught into D. I naught into D is the average value. Like this. Now this average value has to flow here always continuously. Then only the PV panel will behave in a way where you can draw maximum power from it. In order to make buck converter operation for maximum power point tracking meaningful, we need to have the terminal current flowing out of the PV module as continuous, so that peak power point can be tracked at every instant of time. So which means that through the terminals we would like to have IT average amount of current flowing continuously from the PV module. How do we do that? So let me do some modifications here. Let me erase this and also that, and here I will place a capacitor. So let me place a capacitor here, CT. The current that is flowing here, I will name it as IT, as it was originally IT, which was flowing into the Q when the capacitor was not there. And this current I will rename that as IT average, and I'm going to draw another waveform section here, and I will call it what is the current through CT. Now note that the current through the capacitance will have 0 average, just like the voltage across the inductor is 0 average voltage within the cycle in the steady state. So in the steady state, the current through the capacitance will be 0. Now IT waveform is like this, the shaded one, blue shaded. We want IT average to be what is marked here, IT average continuous DC. So if IT average is flowing continuous DC, during this time actually no current is being demanded from IT because Q is off. So what should happen during this time? This portion of the energy should be dumped into the capacitance. So that is what is happening. That portion of the energy gets into the capacitance, and during this portion IT average is coming out from the PV panel and the excess portion is coming from the capacitance. So the capacitance current we can draw like this. So this portion, this is the excess portion above IT average. So during the time when Q is on, IT average is contributing up to this line, blue line, and above that the stored charge in the capacitor is contributing this. So these two add up to give you IT. And during the 1 minus dTs period, IT average is continuing to flow out of the panel, but as Q is off, it is going entirely to charge up the capacitance CT. So it is flowing into CT. Of course, this area should balance out this area. And it repeats likewise. So this portion of the area corresponds to the area here above the IT average line, and this area corresponds to this area below the IT average line. So if you take IT average line as the zero line, above and below the wave shape is exactly what would flow through CT, and it repeats for the cycle. This height down will be same as this height, and that is IT average. So if you connect the capacitor in this fashion, then you can ensure that a current equivalent to IT average is continuously flowing. A DC current is flowing here such that peak power is being drawn from the PV module at all times, and when IT doesn't flow, when Q is off, it is being dumped into the capacitance, and the capacitor is acting as an energy buffer. So this placement of the capacitance here is very important in the case of the buck converter. In the case of the boost converter, this problem did not arise because the inductance was on the input side and there was a continuous current flowing through the inductor. However, one can put a capacitance at the terminals of the PV module. It will improve the ripple, and it will make the input voltage much more stable. It will stabilize the voltage. However, it is not mandatory for the boost converter, but for the buck converter, placing the capacitance is mandatory, is compulsory. Let me mark the voltage across the CT as VT. It is the terminal voltage, and we are interested in finding the input impedance from the PV panel side. So as seen from the PV panel, from here would be the resistance of interest RT, and we would like to find the relationship between the resistances RT and R0. So let us first find the voltage input-output voltage relationship. So it is given by taking the average voltage across the inductor as 0 cycle by cycle in the steady state. So we know from the waveform Vt minus V0 into dTs will be this area, minus V0 into 1 minus dTs will be this area. So we'll just put that down because this area should balance out this area. So we'll say Vt minus V0 into dTs plus minus V0 into 1 minus dTs should be equal to 0. This implies that V0 is equal to Vt into d. We'll mark this as equation 1, the current relationship, and we found that from this waveform, IT average is nothing but I naught into D would give you IT average. So IT average is I naught into D, or can write I naught is equal to IT average by D, and this we will name it as relationship 2. We are interested in finding the resistance relationship, input output resistance relationship. So 1 divided by 2, so we'll give you R naught, which is V naught by I naught, which is equal to VT divided by VT by IT average, VT into D by IT average by D, which will give you VT by IT average into D square. We know VT by IT average, the voltage across the terminal divided by the continuous current that is flowing through the terminal, which is IT average, is the input impedance RT as seen from the PV panel. So that is RT into D square. So rewriting, you can write RT is equal to R naught by D square. So this is the important relationship between R naught and RT that we have been looking for in the buck converter. So RT is a function of R naught and D, which is the control input to the buck converter. So D is coming as a control input by controlling the on-off duty cycle of this Q here. Let us now understand the effect of the input-output relationship of the buck converter on the IV characteristic of the PV panel. So I will put VT on the x-axis. On the y-axis, for the buck converter case, it is IT average, because you have to take the equivalent continuous current that is flowing out of the PV panel. So let me draw a sample IV curve and also a PV curve, power versus voltage curve. And let me take a load line like this. This is 1 by RT. Apparently this RT is adjusted such that it is at an operating point which is the peak power. We would like the PV panel to operate at this operating point or at this load line. So for the buck converter, we have seen that RT is equal to R naught by D square. D is the control input, R naught is the output resistance or the load resistance, which is not under your control. So if D is made 0, whatever may be the value of R naught, RT will be infinite meaning open circuit, and therefore the load line will align itself along the x-axis. So if we draw that, this load line is RT at D equal to 0. Likewise, if we make D is equal to 1, then RT is equal to R naught, so it will result in a load line with a slope 1 by R naught at D is equal to 1. So you see, for the buck converter, all these highlighted zone is the range of the buck converter. All these are reachable points with different values of D varying from 0 to 1. You can have different sloped load lines from 1 by RT with slope of 0 to 1 by RT equal to 1 by R naught with RT equivalent to R naught at D equal to 1. Now here in this case, in this figure, you see that this line which results in the peak power, the peak power operating point lies in the zone of operation of the buck converter, which means this point, this peak power operating point, is reachable by the buck converter. Now if I mark the extreme operating point at 1 by R naught and drop a vertical, you will see that these are the powers that can be drawn from the PV panel at various operating points, and you see that the peak power operating point is within the range. Therefore, in this picture, the buck converter is a meaningful design. However, again, like in the boost converter, I am going to raise a caution. Let me draw another VT versus IT average graph. So you have this typical IV and the power curve, and this is supposed to be the optimal load line for peak power point, and I have here the load line corresponding to D equal to 0, which is where RT is infinite, open circuit. And let us say I have another load line 1 by R0. So this is the other limiting. Instead of being here, R0 value is such that the slope results like this. So this is what you would get at D is equal to 1. So for the buck converter, apparently all load lines will fall only within these two limiting cases, and this would be the range, the reachable operating points. And from this extreme point, if I drop a vertical, and I will see that only these are the powers that can be outputted from the PV module, but the peak power operating point is somewhere here, and the peak power falls here, which is outside the zone of operation of the buck converter. And therefore this scenario would lead to a situation where the buck converter operation is not meaningful. Whatever may be the duty cycle, the control input, the buck converter will not provide a load line which will give a peak power operating point. So you have to be very careful when you design the converters, whether it be boost, buck or any other converter. The load line analysis has to be done first to ascertain whether that particular converter can really provide maximum power point operation. You should, for the buck converter, have a scenario like this where the extreme 1 by R0 slope line, that is the load line slope, is such that the range of operating points should allow for a possibility of peak power point operation, so that the peak power can be drawn from the PV panel, which means peak power point operating point should be a reachable point for the buck converter zone of operation.